We're in 2.7 and this is example 3. Find the derivative of f of x equals 1 over 2x minus 1 at x equals 3. And so we're going over the definition of a derivative, and we have two different definitions. And I'm going to go and do this problem with definition 2/4, or in other words, the h limit definition. If you'd like to use the one as x goes to a, that is fine. Alrighty, so I have f of a plus h, which is f of 3 plus h, since our a is 3 in this problem, minus f of a, which is f of 3, and that's all over h. Now, by the way, you do need to memorize this definition. It's not provided. It's important. Should have the other one memorized too. So here we go. We need to use our function and plug in what is being indicated. So for the first term, f of 3 plus h, I'm going to put a 1 over and then 2 parentheses, and then instead of x, it's 3 plus h, all that minus 1. f of 3 I could do side work, or just plug it in to the function directly within this limit definition of derivative. So I have 2 times 3 minus 1. And now that's all over h. So seeing if I can simplify anything right off the bat, I'm going to go ahead and distribute the 2 in this down low here, and I'm going to get 6 plus 2h, subtract the 1, and so then I'll end up with 5 plus 2h minus the value I get for the second term is 1/5, and this is all over h. So next thing, again, if you plug in h, you're going to get 0 over 0. It happens every single time for the definition of a derivative at x equals a, all the time. So, don't even bother. You need to simplify this, just like we had these limits before where you got the indeterminate form 0 over 0. So my personal favorite way to do this is to multiply by the LCM of 5 plus 2h and 5. So that's going to be 5 times the quantity 5 plus 2h. And then you have to multiply by with the same thing in the denominator. So it's equivalent to 1 times 1. So when I do this, notice that when you multiply fraction by fraction overall, this bottom part's going to just go straight over, leave it in factored form. This top part is like this stuff over 1, and I'm multiplying through to these other fractions using distributive property. So that's going to appear only on the top. It's a common mistake for students to want to put it in both the numerator and the denominator of the fractions that are on this top of this overall fraction. So what we get here is 5 parentheses 5 plus 2h times 1, so I'm not going to bother to write that in, and then that was over 5 plus 2h, minus the 1 times on top, 5 times 5 plus 2h, and then that's all over 5. Big denominator, just carry over. We have h times 5 times 5 plus 2h. So cancel, this is what this was designed to do, to clear the fractions. So I clear the 5s, I clear the 5 plus h, or excuse me, 5 plus 2h, and the 5 plus 2h. I just put that times 1 there as a reminder that, yeah, we can cancel that and be left with a 1. What do we have now? We got rid of the fractions on top, and we have 5 minus parentheses 5 plus 2h, and then leave the bottom in factored form. Notice that when you distribute the minus, good things are going to happen. We take 5 minus 5 and we get 0, and then we're just going to be left with the negative 2h, which has a factor of h. If that doesn't happen, you made a mistake. So go back and fix it in a legit way, not just like pretending that you're fixing it for real. We'll look at these problems very carefully when we grade to make sure you're doing some algebra that makes sense. Now, I'm supposed to be able to plug in this function that remains and have something that's determinate. So I'm just going to go ahead and drop that limit notation and plug in my h equals 0. And look at that. Works out so nicely. I get negative 2 over 25. And that's the exact answer. Always write your answer exactly if you can. Except when you have word problems, like these velocity word problems. So I'm not going to go over this problem in detail. We're just going to revisit velocity. We talked about velocity in 2.1. And so now we're going to revisit the concept of velocity within this exact definition of a derivative that we have. So recall instantaneous velocity, or when we mean instantaneous velocity, we just say velocity and that's fine, is the slope of the tangent line of a position function, or the derivative of the position function at a particular t equals a value, and the t is replacing the x. So we have this definition 3 from your book of the velocity at t equals a. V of a, so meaning the velocity at t equals a, is the limit as h goes to 0 of f of a plus h minus f of a over h, where f is a position function. So it's the same definition, it's just understood that the function is a position function. And this is what we talked about in 2.1, that if our function is representing the position function, then the velocity is the same as at a particular t equals a value is the derivative at t equals a. So sometimes we write our function as a height function like we saw with that Josephson's problem, or s is sort of the more generic way to write position. So I'm just going to talk about example 4 here, Josephson's revisited. Now we can rework this problem without an estimation. We can just figure out exactly what the velocity of the ball was when it was getting close to Joe, specifically at t equals 7 seconds. So it's like going to take just a tiny bit more than that to hit the ground. So, you know, at t equals 7. So baseball dropped 800 feet from the blimp. Height at time t is defined by h of t equal negative 16 t squared plus 800. We found it took about 7 seconds to hit Joe's face, unfortunately, is what happened. Find the velocity of the ball at 7 seconds exactly. So here we're using our newfangled definition, and we're plugging in our function with 7 plus h, replacing the t is, I think, the variable I use, yep. And then we minus h of 7. So expand, simplify on the top, and you end up with a pretty simple function that you can factor out in h, cancels with the h in the denominator, plug in h equals 0, and we get exactly negative 224 feet per second, which was pretty close to what we estimated. Actually, I think that's exactly what we estimated. But now we know exactly at t equals 7 seconds that that was the exact velocity. And we're certain about it. So just when you have these problems on your homework, now you know you can use this definition in 2.7. So what if we wanted to know the velocity at many times, say at 2 seconds, 3 seconds, 4, and 5 seconds? So then it makes sense to get a formula for the velocity and then plug in those times. And that's exactly what we're going to do in 2.8. is to find a derivative function or a velocity function. And then if you're trying to find that derivative or velocity at several times, then you can just do that after the fact, and that's going to be more efficient. That's it for 2.7.